Вань, привет, кстати.
Гриш, привет.
Hey, Grisha.
Я.
Nice to meet you. Nice to see you.
Okay, so shall we start? All right, so the speaker of today is Shinnosuke Okawa from Osaka University, and he will tell us about moduli space of the semiorthogonal decompositions. Please.
Thank you very much for the introduction, and thank you very much for the invitation. Before I start my talk, let me upload the files of my slides again to the chat. Okay, let me start. So today I will talk about my joint work with Peter Bellmans and Andrea Ricolfi, and it's about semi-orthogonal decompositions of derived categories of coherent sheaves. And we take some moduli theoretic point of view. Okay, let me start. So we are interested in triangulated categories, but mainly we are interested in the bounded derived category of coherent sheaves on Noetherian scheme. So this is a typical example of triangulated category. And we will also use its triangulated subcategory perf(x), which is the triangulated subcategory consisting of perfect complexes. These are objects which are locally quasi-isomorphic to a complex of locally free sheaves of bounded length. And the famous theorem by Sell says that this inclusion is equality if and only if X is non-singular. And we are interested in the so-called semi-orthogonal decomposition, which I will simply write SOD, of triangulated category T. And SOD, in a word, is a decomposition of the triangulated category into smaller triangulated subcategories. And general interest, at least for me, is to understand the general properties of SODs. And if we understand general properties of SODs enough, then sometimes we can use these properties to classify possible semi-orthogonal decompositions. And one of the motivations to study semi-orthogonal decompositions of, let's say, the bounded derived category of coherent sheaves is because SODs of this triangulated category is very closely related to the geometry of the variety X. And what I would like to talk about today particularly is the behavior of SODs under deformations of the category. I mean, when we deform the triangulated category, I want to discuss what happens for SODs. And more precisely, we consider moduli problem for this. So let me briefly start with the reminder of SODs, and let me quickly give some examples of SODs to motivate what I will be talking about later. So if we have a triangulated category T, an SOD of T, okay, we first consider SOD of length 2 of a triangulated category. And it's just a pair of triangulated categories, let's say A and B, such that there are two conditions. The first one is there should be no morphism from an object in B from an object to an object A. Sorry, there should be no morphism from B to A. That's the first requirement. And the other condition is that A and B together should generate the triangulated category T, which means that for each object E in the triangulated category T, there should be a distinguished triangle of this form. I mean, there should be a distinguished triangle such that the first object is in B and the second object is in A. So this is a decomposition of the category by B and A. And we simply denote this situation by this notation. So here are some remarks. So actually, I said that T is decomposed by A and B, but actually B is determined by A because B is nothing but the subcategory of objects E such that there is no morphism to any object of A. And likewise, we can recover A from B. So actually, one of these two determines the other. And another remark is, so in this triangle, we had objects B and A. And actually, these objects B and A are uniquely determined by the object E. The uniqueness is easy to show. And actually, from this observation, we get projection functors, PA and PB, from T to A and B. I mean, which sends E to A and E to B. And actually, these projection functors are adjoints of inclusion functors. So we get adjoint pairs like this. And actually, the triangle, this triangle can be understood as the natural one consisting of the adjoint co-unit and unit map. So this was about SOD of length 2. And more generally, we can think of SODs of length L, where L is at least 2. But it's inductively defined in terms of the length. I mean, an SOD of length L is simply a pair of an SOD of length 2 and an SOD of the second component by L-1 components. So we can induct on this. And this situation is simply denoted by this notation. So A1 is the same as the first component, and the rest spans B, the second component. So actually, the information of B is redundant, but this is an easy way. This is a quick way to define SOD of an arbitrary length. So let me give you some examples. So let's assume that we have a base field and the triangulated category is defined over the field so that home spaces are vector spaces and so on. And under this situation, we say that an object E is exceptional if it satisfies this condition here. I mean, we assume that from E to E, there is only one-dimensional home spanned by the identity. And for I different from 0, we assume that there's no morphism like this. And once we have an object like this, then we get an SOD of the triangulated category T. One of the components is the subcategory spanned by E. And the other one is its left orthogonal complement. And this subcategory is simply the smallest triangulated subcategory which contains the object E. And actually, if E is an exceptional object, this subcategory turns out to be equivalent to the derived category of finite dimensional vector spaces. So in this sense, this is an SOD where the first component is as small as possible. And actually, conversely, if we have an SOD such that the first component is equivalent to the derived category of vector spaces, then actually A, it's spanned by an exceptional object. It's simply the object corresponding to this complex here under the equivalence. I mean, this is the K itself sitting in degree 0. And we have plenty of examples in geometry. So let's take X be smooth projective and define over a field which is algebraically closed for simplicity. And let's assume that the sheaf cohomology of the structure sheaf is 0 for I bigger than 0. This is satisfied, for example, if X is a variety of phenotype in characteristic 0 by the Kawamata-Fivek vanishing. Or, I mean, so we get this kind of, so we get this typically on Fano varieties, but this can also happen on, let's say, fake projective planes. And in this case, it's immediate to see that any line bundle is actually exceptional in the derived category. This is because for the derived category, home from E to F shifted by I is naturally isomorphic to the ith X group from E to F. So with this in mind, it's very easy to observe this. So we have many examples in geometry. And let me give you one concrete example. So let's consider the derived category of P2. Then T admits an SOD of length 3. And each component is spanned by O, O1, and O2. All of these are exceptional objects. And this is something called full exceptional collection. And it's due to Baileyson. And actually, already on P2, we have infinitely many exceptional collections consisting of 3 objects. And the classification is quite non-trivial. Actually, there's a one-to-one correspondence between an SOD by 3 exceptional vector bundles and solutions of this Diophantine equation, which is called Markov equation. So each such exceptional collection gives a solution. It's actually simply the ranks of the vector bundles. And this is one-to-one correspondence. And yeah, this is known in a different context. I mean, this has a relationship to Diophantine approximation. And there's a famous conjecture, which is still open due to Frobenius, which says that a solution of this Markov equation is uniquely determined by the max of the triple. This is still open. And under this one-to-one correspondence, we can rephrase this conjecture as a conjecture for vector bundles on P2. So I just wanted to tell you about this because as you see here, SODs are something quite interesting and deep already for the projective plane. And this was about P2, but more generally, for any Del Pezzo surface, there's a full exceptional collection, I mean SOD, where each component is spanned by an exceptional object. And actually, there are such collections with a stronger property. I don't explain this stronger property. And I mean, so this is, we assume that the helix spanned by the full exceptional collection is acyclic. We assume some vanishing conditions on X groups. And So on each del Petzl surface, we have an exceptional collection like this. And so if we deform del Petzl surfaces even into non-commutative direction, those exceptional collections get deformed. And also the helix generated by these exceptional collections also get deformed. And those deformed helices are actually something so-called Artin-Shelter regular algebras, which are studied in non-commutative projective geometry. So yeah, I wanted to say that, yeah, people study non-commutative del Petzl surfaces from the point of view of Artin-Shelter regular algebras. But actually, these algebras come from deformations of particular kind of SODs. So this is one of the reasons why it is important to study deformations of SODs. This is one of the motivations. Now, let me very briefly recall decay hypothesis. This is another motivation. So I think there are many versions, but let me state just one version. So decay hypothesis very roughly states that if there's a step of an MMP, I mean the divisorial contraction or a flip or a Mori fiber space, then there should be an SOD of the derived category of X such that one of the components is equivalent to the derived category of the one you get after the step. But there are, I have to give some remarks here. So to start with, if X and Y, if X or Y is singular, then the bounded derived category is not very nice. And we have to replace this with a triangulated category, which is smooth in the categorical sense. And this is achieved, for example, when X has a quotient singularity. If X has a quotient singularity, then we can replace the quotient singularity by a quotient stack. So we take a stack resolution, which is étale in codimension 1, and we take the derived category of coherent sheaves on the stack. And stack is smooth as a stack, and the category is smooth, at least in characteristic 0. So this is a typical way of replacement. But for general singularities, it's not yet known how to modify this category. And I think this is one of the biggest obstruction in this direction of study. But anyway, this is the first remark. And actually, decay hypothesis is stated more generally for a birational map, such that there's an equality or equality between the canonical divisors. If we take the common resolution and compare the pullbacks of the canonical divisors, and if we have an equality or equality like this, then there should be an embedding or an equivalence corresponding to the direction of the inequality. And what I wrote here is something tautological, so maybe I just skip. And a typical example of this is due to Orlov. So let's consider a blow-up of smooth variety along a smooth center. Then this is a divisorial contraction, as you know. And in this case, the derived category of X upstairs is decomposed into several pieces. And one of the components is equivalent to the derived category of the target, Y. And the others are equivalent to the derived category of the center. So this is the typical example. And in particular, if we take Z, the blow-up center, to be a point, and Y to be a smooth surface, then the derived category of X is decomposed into the derived category of Y, and the category spanned by the exceptional object, which is the line bundle of degree -1 on the exceptional curve. And this is for smooth blow-up, but there are similar results for standard flips and also projective bundles due to Bondau and Orov. And there are many more results for more complicated extremal contractions. There are many works, so I don't remember, but. So these were motivations to consider SODs. So now let me go to the main theme of this talk. So we are interested in, we will introduce the moduli space of semiorthogonal decompositions. But before saying anything about it, let me give you one prototypical example. Let's consider a family of a smooth family of projective cubic surfaces. If we have a family like this, then we can associate the Fano scheme of lines. So this F is the moduli space of lines in the fibers of this family. So in particular, if we take a point B here, then the fiber over B is identified with the set of lines in the fiber, in the cubic surface parameterized by the same B. And as you know, each cubic surface has 27 lines. So this morphism pi is a finite and étale morphism of degree 27. And the monodromy group is related to the Y group of type E6. So this is a very classical subject of study. Now, let me relate this to semiorthogonal decompositions. So as I told you, a point in a fiber corresponds to a -1 curve on the cubic surface XB. But a -1 curve can be identified with the exceptional object, the line bundle on the -1 curve in the bounded term category. This twist here is a bit conventional, but anyway, L can be identified with the exceptional object. So the moduli space of lines F can be actually, so F is the moduli of lines, but at the same time, we can say that F classifies SODs of the fibers, SODs of the cubic surfaces of this family. And here we consider particular form of SODs, of this form. One of the components is given by the exceptional object given by the line. And the rest is, the other component is the semiorthogonal complement. So yeah, so F can be regarded as a parameter space of semiorthogonal decompositions. And actually, this F here is an open and closed subspace of the moduli space, which classifies SODs of the fibers of this family of cubic surfaces. So this is the prototypical example to keep in mind. So now I want to introduce the moduli space of SODs, but before that, I need some preparation. So the first definition is, let's assume we have a morphism of schemes. And suppose that we have an SOD of the perfect derived category of the source. Then we say that this SOD is F linear or linear over the base if for any object on the target, the pullback of that object tensor with an object of A is contained in A. And this is equivalent for B. So we assume that A and B are stable under tensoring by the pullbacks of the objects on B. So this is what we call linearity. And this is a small remark, but sorry, this condition is actually automatic when B is the spec of a field or a spec of dVr. But in general, this is a non-trivial condition. Next, we need a lemma about pullback of SODs. Let's consider a smooth projective morphism of schemes. And let's assume that we have an SOD of X. And let's assume it's linear over the base, as we assume, the notion which I just introduced. And so this is the morphism we are interested in. And let's assume, let's take a morphism from U to B and take the base change like this. In this situation, actually, we can define an SOD of the fiber product like this. I'm not giving the details, but I just wanted to say here that if we have an SOD on X, which is linear over B, then there's a well-defined notion of pullback SOD on the fiber product, which is linear over U. So we have the well-defined notion of pullbacks of SODs. And once we have the notion of pullbacks for SODs, we get a pressure shift. We get a pressure shift from on the category of affine schemes on B, which is defined like this. For each affine scheme on B, let's say U, we take the set of SODs of the fiber product, which is linear over the base. And by the pullback of SODs, this becomes a pressure. This becomes a contravariant functor from the category of affine schemes over B to the category of set. And actually, a theorem here is if the morphism F from X to B is smooth and proper, and we assume that B is an excellent scheme, and we also assume that there is a relatively ample invertible sheaf on X. Under these conditions, actually this holds more generally, but at least under these conditions, it follows that this pressure is a sheaf with respect to the étale topology. So this SODF prime, which I just defined here, is contained in the category of sheaves on the big affine étale side. And so let me give a comment on this theorem. So we gave a proof under the assumption that the base scheme is defined over Q, defined in characteristic 0. And our proof was reduction to the so-called Elegans Galois descent for SODs. But finite groups are not necessarily linearly reductive and positive characteristic. This argument holds only in characteristic 0. But at the same time, Anthew and Elemental proved this without the assumption on characteristic, and they used a method from derived algebraic geometry. But anyway, it follows that this pressure classifying SODs is a sheaf on the big affine étale side. And actually, there's an equivalence between the category of sheaves on big affine étale side and the category of sheaves on the big étale side. Here's the difference. It's about sheaves, so we can drop. If the values are defined on affine schemes, the values are automatically defined on any scheme. So this way, we get a sheaf, étale sheaf on the category of schemes over B. And this is what we call the moduli functor of semiorthogonal decompositions. And here comes the main theorem. So this is together with Peter Bellmans and Andrea Ricolfi. So let F be as above. I mean, smooth and proper morphism between excellent schemes with relatively ample invertible sheaf on X. Then this sheaf classifying semiorthogonal decompositions is actually an étale algebraic space over B. So here we are claiming that this sheaf in étale topology is actually an algebraic space over B. And moreover, it is étale over B, meaning that the structure morphism from this algebraic space to B is smooth of relative dimension 0. If you remember, we had the example of the Fano scheme of lines. So it was an étale finite morphism. And we cannot say in general that this morphism is a finite morphism, but we can say that at least this is always étale. And this SODF is an algebraic space. So this is the main theorem. And let me explain how we should interpret this. So actually, this looks a bit abstract, but actually this functor classifies something reasonable. I mean, if we take a quasi-compact and separated scheme over B, then the set of values over such a scheme is the set of SODs of the base change, which is linear over the base. So for any reasonable scheme like this, this moduli space classifies reasonable things. And this in particular implies that if we take any closed point of the base, then the fiber over the base over the point is in bijection to the set of SODs of the fiber. So here is the picture. So we started with some smooth projective family like this. And starting from such a family, we constructed some algebraic space, SODF. And we proved that this is étale over B. So the morphism from SODF to B is almost like a covering space, but it is not in general, in the sense that there might be non-separatedness like this, and also there might be some puncture. In some places, specialization may not exist. But at least this is étale, so it's like a local homeomorphism. And if we take a point from the base space, then the fibers, so here we get the fiber, and the points in the fiber are in one-to-one correspondence to SODs of the derived category of the corresponding fiber. So this is why we call this algebraic space is called the moduli space of SODs. So here's what I just mentioned. Okay, so let me give you a bit more interpretation. So actually, we proved that, I mean, the main theorem implies the following. So for each fiber of the morphism, any SOD of the derived category of the fiber always and uniquely deforms to nearby fibers. I mean, étale locally over the base. This is simply because the main theorem says that the morphism from the moduli to B is étal. So if we take a base point, and if we take a point in the fiber, then we can always find a local section. And we can always take an étal local section starting from this point. And the modular interpretation implies that we can deform the SOD on the central fiber étal locally over the base. But of course, in general, we cannot extend this section globally because this covering space may have monodromy, non-trivial monodromy. So the section exists only locally. So this is what we proved. I mean, this is a consequence of the main theorem. And so this sounds like infinitesimal statement, but in the main theorem, as I stated, we proved the global existence of the moduli space. And this global existence is actually useful, has a few consequences, as I will explain next. And here's one remark. So in general, the structure morphism from the moduli space may not be separated. And the example is actually not pathological. If we consider the isotrivial degeneration of the quadric surface to the Hilbert surface of degree 2 and take the associated moduli space, then actually it's not separated. This is very much related to the talk by Hokuto Uehara on the other day. And also this morphism here may not satisfy the existence part of the valuative criterion. I mean, the valuative criterion for properness. This may not be satisfied. And an example is obtained by considering a degeneration of classical Enrique surfaces to singular or supersingular Enrique surface, which exist only in characteristic 2. And this is also a counterexample for the invariance of genera. So we don't know if there's a counterexample for this part in characteristic 0. I mean, we know the example only in characteristic 2 or in mixed characteristic. This is an interesting question in characteristic 0. Now, let me say a few words on the proof. So we want to prove that the functor classifying SODs is an étal algebraic space. And for this, there's a very useful criteria due to Mike Artin and later generalized by Hall and Reed, which is as follows. So let B be an excellent scheme, and let F be a sheaf on the big étal side of schemes over B. Then such a sheaf F is an étal algebraic space over B if and only if these two conditions are satisfied. One of the conditions is F is locally of finite type. So this is not so difficult. And what's more interesting is the second condition, which says that the natural restriction map like this should be bijective. And here R, here. So here this R is a complete Noetherian local B algebra. I mean, B is the base field, base scheme, sorry. So this is a restriction map from the set of sections over spec R to the set of sections over the closed point. So here it is required that given a section over the closed point, it should always and uniquely extend to a global section. And this is sort of the essential part. And in order to prove this second statement, so we had to establish certain deformation theory. And this is by us and jointly with Wendy Lowen. And we had to establish a deformation theory to prove that for each n, the map between n plus first step and the nth step is bijective. And yeah, let me explain this a bit. So idea is as follows. We are interested in semiorthogonal decompositions of x, of the base change of x over Rn. But in order to study SODs of the perfect Dirac category of XRn, we can look at the distinguished triangle of kernels of the projection functors. I mean, as I explained before, SOD will give the pair of projection functors to A and B. And these projection functors are given as integral transformations. And the kernels of the integral transformations makes a distinguished triangle like this. So the transformation by KB will be the projection functor to B, the subcategory B. And the the integral transformation by KA will be the projection to A. So we can rephrase SOD as a distinguished triangle. And because KA is determined up to isomorphism as the cone, this is typo, KA is simply the cone of the morphism S here. It's enough to consider the deformations of this bit. But we always consider deformations such that the target is the structure sheaf of the diagonal, because the structure sheaf of the diagonal is the kernel for the identity functor. So in the end, we'd like to study the set of morphisms like this, whose restriction to the nth step is the morphism S we started with. So this is a deformation theory of morphisms in a Dirac category, where the deformation of the target is fixed. I mean, here we fixed the deformation of this deformation of the structure sheaf of the diagonal to be the structure sheaf of the diagonal. And this kind of deformation theory wasn't available in the literature, so we had to do this by ourselves. And this generalizes deformation theory for fault functors and also stable pairs. So I guess this is something interesting on its own. But in any case, so we established the deformation theory, and the upshot is as follows. So a deformation estuadal of S exists if and only if the obstruction class vanishes, and the obstruction class is defined as an element of this particular vector space. And if the obstruction class is 0, then the set of lifts up to isomorphism is a tosser under this vector space. So in order to understand this map here, it's enough to understand these two vector spaces. But actually, in our situation, our home itself turns out to be 0. So any X group from here to there is 0. So actually, this is 0 and this is 0. And the vanishing of this space means the unobstructedness, meaning the surjectivity of this map. And the vanishing of this space means the uniqueness of the lift, which is the injectivity of this map. So this way we can show the bijectivity for each step. And from finite, to go from finite to infinite, we need some sort of algebraization theorems, but these were already in the literature. So yeah, this is how we prove this kind of statement. Now, let me say a bit more about separatedness of this, the separatedness of the structure morphism. As I said before, this is not separated in general, but if we know that this is separated, there are some applications. So the first one is as follows. Let's assume that the structure morphism is separated. Then actually it follows that the moduli space is a scheme. So far, we don't have any example where the moduli space is not a scheme. But in general, this is not separated, so we cannot use this argument. This is a general fact about algebraic spaces. I mean, if there is a separated and étale morphism from an algebraic space to a scheme, then the algebraic space must be a scheme as well. And this happens in particular if the base space is the spectrum of a field. And in this case, this is again a general fact about algebraic space. And if the base is the spectrum of a field, then the moduli will be simply the disjoint union of spectra of fields, where each field is a finite and separable extension. So this is something we observed. And then Sasha Efimov pointed out an interesting corollary of this, which is about the field of definitions of SODs. It's like this. So let's assume that X is a smooth and projective variety over a field. And let's take any field extension and assume that the derived category of the big base change has an SOD. Then it follows that there's a finite and separable intermediate field extension and an SOD of this small extension such that the given one is the base change of this SOD defined on the smaller field. Well, as far as we know, the only way to prove this kind of statement is to use our main theorem. And this finite extension is necessary. I mean, in general, the SOD here might have non-trivial monodromy, as we observed in the example of the family of cubic surfaces. So we have to take a finite field extension to kill the monodromy. But finite is enough. That's the point. So this is one application of separatedness. And the next point is due to Pyorchkov. This is a very nice observation, I think. So let's assume that the structure morphism is separated, and also assume that the base scheme is connected. And let's take a base point. Then the restriction map like this is injective. So what is this restriction map? So on the left, we have the set of SODs of the total space, which is linear over the base. And if we have an SOD of the total space linear over the base, we can restrict it to an SOD of the fiber over B to get an SOD of the fiber. And the claim is this restriction map is injective, meaning any SOD of the total space is uniquely determined by its restriction to one fiber. And this is quite easy because if we have an étale morphism, which is separated and the base is connected, then then the section is uniquely determined by its value at the point, right? I mean, if we have a separated and étale morphism like this, and if we fix a value at the point, then there's only one way to extend the section. If it's not separated like this, then the section may not be defined by the value at the point. But if it's separated, it's uniquely determined. And via moduli interpretation, this means that the restriction map like this is injective. And the separatedness, so he also pointed out that this kind of separatedness is true if the morphism we started with is an isotrivial deformation. And this is easy to show using the base change property of our moduli space. It's a fine moduli space. So, and yeah, and as an immediate corollary, we can recover an old proposition by myself with Kawatani, which says that if we have an SOD of a smooth projective variety, and if we take a line bundle, which is numerically trivial, which is in the neutral component, then tensoring by such a line bundle preserves the components of the SOD. And this kind of statement is useful for classifying SODs. In particular, by using this, we can prove that the derived category of a bielliptic surface has no non-trivial SOD. And this simply follows from the fact that the canonical line bundle of a bielliptic surface is contained in the neutral component. And yeah, with Kawatani, we gave a bit technical proof, but now this can be immediately proved using this observation. And Piroshkov himself gave many more results using this kind of technique as a tool. And in particular, he proved the non-existence of the so-called phantom categories in many surfaces, like the Petrel surfaces or geometrically ruled surfaces. These were folklore conjectures, and there was no general strategy. But yeah, he gave a very nice proof for these kind of statements. Finally, let me say a bit about a comparison to extremal contractions. So again, let's take a smooth projective family. So in our main theorem, we proved that any SOD on one fiber always and uniquely deforms to nearby fibers. That's one of the consequences. But decay hypothesis says that there should be a correspondence between SODs and extremal contractions. So if SODs always deform, it's natural to ask whether extremal contractions also always deforms. And actually, this was something studied by Kolar and Mori in a paper from 1992. And they proved that at least over the field of complex numbers, that an extremal contraction of a fiber always and uniquely deforms to a family of extremal contractions of nearby fibers. The proof uses a relative version of vanishing theorem. So this is, I think this is known only in characteristic 0, but anyway, they proved a statement like this. So both extremal contractions and SODs always deform. So I would like to propose that I guess it's reasonable to reformulate decay hypothesis as a claim that there should be a functorial morphism like this, a functorial morphism from the moduli space of extremal contractions of X relative over the base to the moduli space of SODs. And the morphism decay associates extremal contractions to relative SODs. And yeah, let me say something a bit finer. So if the morphism is not smooth, then it's known that then it's possible that an extremal contraction on a fiber deforms to identities. I mean, if the family is singular, it's possible that non-trivial extremal contractions deform to trivial extremal contractions, meaning identities. And likewise, there is an example of non-smooth morphism and an SOD of the total space such that the component is non-trivial, but it's trivial on the general fiber. I mean, if F is not smooth, there is an example where one of the components of SODs is concentrated in the central fiber. This is what I'm saying here. And these two are somehow comparable. And an interesting question here is, if the morphism is smooth, can we say that if the decomposition is non-zero, then it's non-zero on the general fiber? Put differently, if F is smooth, can we say that if, how to say, I mean, so we want to show that if F is smooth, then the concentration of the component in the central fiber never happens. That's what we want to prove. Yeah, we stated this as a theorem in some occasions, but it turned out to be, I mean, there was a gap in the proof and it's still a question and we are working on it. And this would have further applications for the classification of SODs. And we, again, by the analogy between SODs and extremal contractions, we expect this question to be true because for extremal contractions, there is a theorem by Wisniewski, which says that if one has a smooth variety which is not minimal, then its deformation is not minimal again. So this result by Wisniewski, I mean, if we expect that the corresponding statement, I mean, a statement which corresponds to this one holds for SODs, then I guess it's reasonable to expect this question to be the case. Okay, that's all what I wanted to say. Thank you very much.
Okay, thank you. Any questions and comment?
Any explicit results about smooth Fano threefolds?
Sorry, what kind of result do you mean?
Similar. What?
Okay. How to say? I'm not sure if I'm answering your question properly, but there's an example like this consisting of a family of singular Fano varieties. It's an example due to Totaro. I mean, it's about the jumping phenomena of Nefcons.
Yeah. Okay, yeah.
Okay. right, any other questions? All right, I have one basic question about this Markov equation. So do you know what the motivation of the Frobenius to propose his conjecture?
So this statement is equivalent to another conjecture about Diophantine approximation. So I guess that's one of the motivations. Sorry, I can't remember the precise statement of the other conjecture, but yeah, there's an expository book about Frobenius conjecture. And yeah.
So it has something to do with the geometry.
Well, you know, the question itself is purely algebraic or number theoretic, but yeah, it would be interesting. I mean, as I told you, the question can be rephrased as a question on vector bundles on P2. So it would be interesting if we can use geometry to prove this kind of question, but I guess so far there's no result in this direction.
Okay. All right. Any other questions? No, if not, then let's thank speaker again. All right, thank you.
Thank you.
Okay.
Yeah.
Thank you. Mhm.
Yeah, thank you. Yeah, sorry, maybe I was a bit too quick.
No, no, no. Perfect.
Thank you.
Okay, so let me quit this room. All right. Bye. Have a nice
Bye,
day.
Jiho. Bye.
Bye.